Okay. So, in the last class we have already discussed about the advantage disadvantage of AM, DSB-SC, but both AM and DSB-SC, if you see how it occupies the spectrum, it is always either suppressed carrier, it will be occupying this entire 2B band. If I put the carrier on top of this, nothing else changes, at least in the frequency domain nothing else changes, still it occupies 2B. But I can see already, if you see the message signal which is getting translated over here and creating this 2B band, it is even symmetric, right. This MF must be a Fourier transform of a real signal. So, it must be even symmetric. So, whatever spectrum component you have, the negative half also, that there will be a symmetric spectrum component. So, I know already that only this half carries the whole information, I do not need that other half. This other half, when it was actually a baseband signal, it was occupying only B band. It is just because of this modulation I have suddenly increased it to 2B, right, and this is just repeating the negative half, which is a mirror image of the positive half. So, it is not required actually to transmit that, I can always get back my signal, we will discuss that later on, through the positive half only, or just one half, either positive or negative, whichever half you require. From that portion only I can extract the whole signal. That is possible, we will show that that is possible. So, if we can employ something where we do not have to actually transmit both the bands, then I can save some bandwidth, because this is the band he will be occupying in the channel. So, 2B is lost from me. If I can reduce it to B, other B, I can actually transmit another signal, and if all the signals are of B bandwidth, then I can actually transmit double the number of signals with the same band, utilizing the same band, right. So, that is why we can now think of employing some bandwidth efficient. So, this will be all processing in the looking at the frequency domain. So, bandwidth efficient transmission or modulation technique. So, that should be our first target. So, to do that, as you can see that I need to get one half of it, right. So, what we will say that if this is MF, I will represent this as one half this and another half this. This I call as M plus F, and this I call as M minus F, that is the negative part of the spectrum and the positive part of the spectrum. And if you just see, if I just add these two, I will get my MF. So, MF is nothing but M plus F plus M minus F, right. So, that is the representation. Okay. So, this representation will be trying to utilize for generating our signal. You will see that the frequency spectrum, how it generates a proper frequency efficient modulation technique. So, we will see from our discussion later on. But to do this, we need to employ another technique or tool that is required to be studied first, then only we will understand how to employ this technique. So, this is called Hilbert transform. Okay. Let us try to understand what is Hilbert transform actually. I am just giving definition now, we will understand why this is really required. So, we are saying Hilbert transform is nothing but, suppose I have a signal xt, Hilbert transform of that signal will be xht, which is nothing but Hilbert transform of xt, and it is represented as this 1 by pi, it is just the definition I am giving. Okay. So, it is of course a function of t, and I have taken that dummy variable for integration alpha, and it is actually x alpha d alpha divided by t minus alpha. If you try to see what this is almost like a convolution. We have already defined what is convolution. It is a convolution of this. So, xt convoluted with 1 by pi into t. Okay. So convolution means it's, suppose I want to convolute m1t with m2t, we have already defined that. So you need to get m1 tau and m2 t minus tau d tau, right? That you have to integrate from minus infinity plus infinity. Similar thing is happening. 1 by pi t is one of the function, let us say m2t, and xt is m1t. If you just do convolution, you will be getting this. Okay. And that instead of tau, we are saying this is that alpha, right? Or if the convolution integration variable is t, then this should be that alpha. Okay. So I can identify immediately that xht is, if I do Hilbert transform, it is nothing but the convolution of xt and 1 by pi t. Why I am doing that? Because we also know, we have we have already discussed about that, that if some signal is convoluted in time domain, if I do a Fourier transform of that, it should be multiplication of those two signals. So if I represent xhf as the Fourier transform of xht, then that must be equal to the Fourier transform. Suppose xt has a Fourier transform of xf, and pi 1 by pi t, we have already defined the Fourier transform of that. Okay. So 1 by pi t is actually, the Fourier transform is minus j signum f. This is something we have defined. We have actually done this thing for signum t. Okay. And then we know also that anything in time domain, if I have a Fourier transform, frequency domain also, the duality property I can use, and if you just utilize those two things, you will see that signum function, the Fourier transform, that signum f, is actually a Fourier transform of minus 1 by j pi t. So from there we get this conjugation, right? So j signum f actually has a Fourier transform, minus j signum f has a Fourier transform of 1 by pi t. So this is something I know. So 1 by pi t, the Fourier transform is minus j signum f, so which is nothing but j xf signum f. So this is something I know about the Hilbert transform. Okay. So if I pass a signal through a Hilbert transform circuitry, so suppose this is my Hilbert transform circuitry. So if I pass xt through it, I will be getting xht. Now I want to get the characteristics of this, that is the hf of this one, that is the transfer function of this one. So I know that xhf, if this is the transfer function is hf, that should be xf into hf, right? So if I just go back to my previous relationship, then what is my hf? If this is the Hilbert transformer, so hf must be j signum f, right? We have already proven that xhf is xf into minus j signum f, therefore hf must be j signum f. So this is actually the transfer function of a Hilbert transform, okay, which I can write as minus j when f is greater than 0 and plus j when f is less than 0, right? Because signum function we have already defined, signum function is nothing but this. Okay. So whenever f is greater than 0, it must be plus 1. So this is plus 1 and this is minus 1, we have already defined that. So this is f. So whenever f is positive, it is plus 1, so that must be minus j, and whenever f is negative, it is minus 1, so that should be minus j into minus 1, that should be plus j. So this is what we get, hf definition, okay, which I can further write as 1 into e to the power j pi by 2, and this we can write as 1 e to the power j pi by 2, right? J can be written as this. Okay. Just put Euler's theorem, we will see that. Okay. Because it will be cos pi by 2 plus j sin pi by 2. Cos pi by 2 will be 0, means if it is this, then it should be j pi by 2, j sin pi by 2, that should be j. Okay. And this will be minus j. So, if you just see, the transfer function looks like this. Any transfer function, this is the transfer function, any transfer function must have a amplitude, this one plot, and a frequency plot. The amplitude, if mod HF I wish to plot, that should be constant, that is 1. If you take mod of this, that is always 1. So, HF has mod of HF, that is always 1, and now the phase 1, let us say theta HF I want to plot. Okay. So, what that should be? That should be whenever f is positive, it should be theta is minus pi by 2. So, that should be minus pi by 2, and this is plus pi by 2. So, this is pi by 2, this is minus pi by 2, right. So, that means whenever I have a positive frequency component, it is actually shifting the phase. See, the amplitude remains the same. So, amplitude I do not touch. Whenever I pass it through this, whichever frequency component, suppose all tones I am passing. So, whichever frequency component is there, for the positive frequency component, it is giving a pi by 2 phase shift, and for the negative frequency component, because the negative frequency component will be exactly opposite, it is again giving a pi by 2 phase shift. So, it is always giving a minus pi by 2 phase shift to every component, every frequency component. So, whichever it is, in the positive it is minus pi by 2, in the negative, because it is already either pi or minus pi. So, it is actually plus pi by 2. If you just take it out, it is again shifting by minus pi by 2. So, it is actually always every frequency component that you give, it is giving pi by 2 phase shift, or I should say rather more concisely, that minus pi by 2 phase shift. So, this is a typical circuitry which does not touches the amplitude, but it just take every frequency and give a pi by 2 phase shift. Okay. So, any frequency component you give, it will just give you pi by 2 phase shift. Here I would like to point it out, there are two different things. We suppose we have a signal, we give a delay. Okay. So, let us say I have a signal xt, which is nothing but let us say it has two frequency component, cos omega ct plus cos 2 omega ct, okay, with some coefficient c1 c2. Let us say I am providing a delay to it. Okay. So, this is c1 cos omega c, delay means it will be delayed by that much time. So, t minus t0 plus c, let us say this is c2 cos 2 omega c t minus t0. Okay. So, let us say I have a circuit through which if it passes, it gets a delay. Okay. So, it just appears little bit later, because the circuitry provides some delay, and that delay is t0. So, if I have that, then what is happening? This particular frequency component cos omega ct, how much overall delay it is getting? Omega 0 t0, sorry, omega c t0, and this frequency component, how much delay it is getting? It is getting 2 omega c t0, right. Different frequency component will get different overall delay. Okay. So, that is the overall delay that they are getting, right. So, sinusoidal will be delayed by this much amount. So, as you can see, different frequency component, sorry, I should not say delay was already t0. So, that is the phase shift we are getting. We should now talk about phase shift. So, basically this particular frequency component is getting a phase shift of omega c t0, and this particular frequency component is getting a phase shift which is 2 omega c t0, right. These are the two phase shift you are giving. If I was passing it through a delay element, whereas when we are passing it through a Hilbert transform, what will happen? Both of them will get equivalent phase shift, all pi by 2. So, both of them, both the frequency component will get equivalent phase shift. So, immediately what will happen? They will have equal phase shift, but the delay will be different for different frequency element. So, that means if a constituent signal is composed by multiple frequency element, they will be separately delayed. So basically after Hilbert transform you will not get back similar signal, whereas here the signals means composition will remain the same. So there is a difference between delay and this one. It works almost similarly because it does not touch the amplitude, it just works on the phase, okay, for every frequency component. But here in Hilbert transform you are giving constant phase shift to every frequency component, where in delay element you are giving constant delay shift to every frequency element. That means not equivalent phase, it will be actually linearly growing with the frequency term. If you just see, the phase element is 2 omega c T0 for 2 omega c frequency. It is actually omega c T0, that means it gets doubled over here and whatever amount it was having over here. So whenever your frequency gets doubled, the phase shift will be doubled. So if you just plot a delay element, that will look like this. Whereas if you plot the Hilbert transform, that will also have amplitude spectrum as this. Mod HF will be this, the delay element will be linear. So whatever is the frequency, it will be just scaling with the frequency term. Okay, if the frequency doubles, the delay doubles. So it will be just linear with 45-degree angle. Okay. Whereas for Hilbert transform, you are constantly giving constant phase shift. Delay will be different. Okay. So there the phase shifter is this. So that's the difference between these two. Both of them, a delay element or a Hilbert transform, both of them actually shifts different frequency with either different phase, or this one gives same phase shifting, and they will not touch the amplitude. But there is a certain difference, and that is why whenever you do Hilbert transform, you will have a deformation to the signal, whereas whenever you do means you provide a delay element, you will never see any deformation to the signal. This is the basic difference between these two. Okay. And as you can see, this is very easy to realize. Okay. That is a circuit which is very easy to realize. Just keep on putting resistor. Whenever it's resistor means it will be just a propagation delay through it. So if you just keep on putting a resistor or a transmission line, your signal will come, it will take some amount of time to come out from the output. So it will just be delayed version of the input signal. So this is very easy to realize, any real circuitry will give you that, as long as it is not touching the amplitude. Whereas this one is harder to realize because it has a frequency selective delay. Different element gets different frequency element gets different amount of delay. Okay. Phase shift is same. So this is some circuitry which is very difficult to realize. Okay. So fine. Therefore, if you wish to employ a circuitry which does this transformation, so all we have to do is we have to understand that to do this I have to take every frequency component and give a phase shift which is pi by 2. Okay. So original delay element will not do that, you have to selectively take, maybe with a very narrow band pass filter, you have to take every frequency element, and for everybody you have to give pi by 2 phase shifter. Okay. So that is what you will have to do. It's means generally it is a difficult circuit to realize. There are techniques, but it is a difficult circuit to realize. But we will see that there is a way to actually bypass this, and we will first try to appreciate that where this is, means why we are discussing that. Of course, we started talking about bandwidth efficient modulation, so why this is required. So we'll probably try to appreciate that part. Okay. So first let us go back to my original proposition, that a signal MF, which is a frequency domain representation of some MT. Okay. So let us say this is my MT. This signal can be represented as this plus this, where this is my M plus F and this is my M minus F, right, okay, where I represent MF as M plus F plus M minus F, right. Now if I wish to do a from DSB a bandwidth efficient one, which is generally originally called as SSB-SC, that means single sideband suppressed carrier. So, what I try to do is, because I know one of them is actually giving me the information, so I wish to keep only one of them. So, when I do modulation at FC, I just put one of them. In the negative half, what should be remaining? It should be the other one, because it needs to be symmetric, otherwise the signal will not be real, and I cannot transmit a means complex signal in the air, right? That is not possible. I cannot even generate a complex signal. This is just representation. Complex signals are representation. Okay. So, if I wish to do that, I should either represent it this way, or I can represent it in another way. Okay. So, this is actually termed as upper sideband, and this is termed as lower sideband, because at the positive half you can see this is actually the lower portion of it. Okay. That's the negative part of it. So, that is why this is called the lower sideband, and this is where you are at the positive half, you are actually transmitting the upper sideband, because there are two sideband. So, this I call as upper sideband and this I call as lower sideband. So, here at the positive half of the frequency, I am transmitting either upper sideband or lower sideband. So, any of these two are valid modulation, if I can do this modulation. First of all, I have to be convinced that this modulation is possible. First, let us try to see the mathematical treatment of it. So, what is this? This is actually, let us first try to represent this m plus f, okay, and then we will try to represent this one. So, what is m plus f? If mf is multiplied by uf, what is uf? Uf is nothing but this, right. So, less than f less than 0, it is 0, almost like ut, okay, it is a unit step function, and greater than f it is 1, right. So, if I multiply this one with this, immediately what do I get? I get only the positive half. So, m plus f must be mf into uf, and similarly m minus f, if u minus f is defined as this, then it should be mf into u minus f. Now, this uf, the good part is, can be represented with respect to Signum function, okay, because Signum function, which is nothing but this thing, okay. If I add 1 to it, then what will happen? This is 1, this is minus 1. If I add 1, this will go to 2 and this will be 0, and then put half. So, if this is my signum f, if I write signum f plus 1 into half, that must be my uf, right. So, uf I can write this way. Why I am doing this? Because I want to deliberately bring that signum f, because I already know that j signum f is the representation of Hilbert transform, or minus j signum f. So, I am deliberately bringing it, okay. So, therefore, now I can write m plus f, which we have written as mf into uf. So, that I can write now as mf into half signum f plus 1, right. This I can write as half just mf plus mf into signum f, right. I can write this way. This is mf, and what is this? So, if I just introduce a j over here, minus 1 by j means 1 by j should be taken over here. So, I can write 1 by j into j mf signum f, right. If I introduce a minus term over here, that should be minus 1 by j, multiply above and down by j, you will get this is actually minus j square, that is plus 1. So, you get just j over here, right. So, I can write half, this is mf plus or minus j, this is mhf, isn't it? there is a sign problem. MF, signum F, I need a minus J, oh that should be plus, yes. Okay. So, this is what we get. So, immediately I can see that this M plus F can be represented as half of MF plus J into the Hilbert transform of the message signal. So, this can be represented. If you just do similar things, you can see also M minus F can be represented as half into MF minus J MHF. You can also do this. Okay. Just similar thing, you just have to represent it, okay, this way. So, now knowing these two things, let us try to represent this SSB with USB. Okay. So, what is this part? This part is just M plus, this is the plus half, F translated at FC, right. So, it must be M minus F minus FC, and this part, what is this? This is M minus, the minus half translated at minus FC. So, that must be F plus FC. Therefore, I can write phi, suppose SSB for the upper sideband. So, U F, this must be equal to M plus F minus FC plus M minus F plus FC, right. This is the representation. If it has to be a lower one, accordingly we will have to do that. Okay. So, this is pretty much clear how I can represent my upper sideband SSB modulated signal, right. Now, all I have to do, this M plus I already have expression. So, I will have to just replace that. So, M plus I already know that M plus is nothing but half into MF plus J MHF, right. So, I will just write that. So, I can write half M plus can be written as MF minus FC plus J MH F minus FC, right, plus this part again I will replace half M F plus FC minus J MH F minus FC, right. That is the representation. Okay. Whichever has J term, I will take them out. So, basically what do I get? I get half M F minus FC plus M F plus FC. So, this is the term which is free of J, and then if I just take minus 1 by J common, okay. So, 1 by 2 J. So, immediately inside I will get MH F minus FC minus MH F plus FC, I get this. Okay. So, this is just algebraic manipulation. What is this? This is the modulation of MT or MF, I should say. So, if I just wish to now do a Fourier transform or inverse Fourier transform of this one, what do I get? This must be represented as MT cos omega Ct. Okay. Of course, that half term will be gone, okay, because with half it will be this. Okay. So, MT cos omega Ct, this will be represented, and this particular term, that should be 1 by 2 J is there, and this is just for the sinusoidal one. If I multiply MHT, if this MHT is the Hilbert transform equivalent time domain signal, if I just multiply my MHT into sin omega Ct, I will be getting the corresponding Fourier transform as this one, because sin omega C will have 1 by 2 J, and then you have those modulation term. So, it will just be translated at plus Fc and minus Fc. So, basically what I can say now by looking at this spectrum. So, here I was doing all the manipulation in the spectrum, because I know that SSB means it should be half of the spectrum, right. So, I can do the manipulation in the spectrum and I have the understanding of Hilbert transform. So, this is what I was having. So, initially that spectrum I have represented with respect to UF. From there I went to Signum F. I knew that with Signum F I can represent it with respect to the Hilbert transform. And then from there I could do some algebraic manipulation and I could see that actual SSB signal is nothing but this. So, that means you take the message signal multiply by cos and you take the Hilbert transform of the message signal multiplied by sine, means subtract these two, you get your SSB signal. So, generation of SSB just comes from this. We have seen the frequency domain representation, now in time domain we can immediately get the representation. Okay. But in the next class what we will try to do, try to appreciate that this MHT, we have already talked about that circuitry to do just 90-degree phase shift for each component is a very difficult one. We will try to devise a circuit which is known as Weber's circuit, which does it very nicely. Okay. So, we will try to see that and try to see the corresponding mathematical representation of that. Thank you.